Take it away.
Thank you very much. Well, I'm afraid I have a tendency of giving one title and putting another one on the transparencies, but I hope you will not get confused. Well, gerbs are algebraic stacks as well. Okay. So this might help. There is actually a reason. So thank you for inviting me to speak here. Giving the maybe doubtful pleasure of being the first speaker, 9 o'clock in the morning. But I'll try to do what I can. So we had those lectures last week. Some of you have heard them. And one of these series were by Ralph, and they were something about two groupoids, two categories, things like this. So I will start to kind of remind you of the people who weren't here to show a few pictures. But before that, so the joint work with Paul Bressler, Alexander Gorachowski, Boris Cygan, and actually it's a continuation of a long program. So let's plunge into it. So two groupoids. So you've seen, if you've been here last week, you've seen the picture. So two groupoid is a groupoid, so has units, has arrows, has also two morphisms. So maps between morphisms, or you should think of it as maps between morphisms. And well, groupoid is groupoid. These two morphisms satisfy some, can be composed with some natural conditions. So there is this horizontal composition where we fix the two objects, and then we look at arrows between objects. And there's vertical composition where we go from, where we compose morphisms and see what happens with two morphisms.
But Ryszard, your pictures are rotated from mine. So what you call vertical, I call horizontal, and vice versa.
Okay, whatever.
Apart from that, it's the same.
Apart from that, it's quite the same, right? Anyway, the horizontal vertical does refer to pictures, right? So that's not much a difference. There will be a slight difference in a moment, right? So canonical example of a two groupoids is a two groupoid of categories. And somehow one should really start from this one. So objects are categories, arrows are just functors between categories, and two morphisms are natural transformations of functors. Now, two groupoids. So like if you have a group, you have a classifying space of a group, and maybe you know that having a group and classifying space of a group is just as good. It's the same thing for groupoids and two groupoids. So to a two groupoid, you can associate a simplicial nerve. So basically, a simplicial composition of space. So I wrote explicitly what it looks like. So the objects, the points of zero simplices are just objects. One simplice is arrows. Then when you start building higher simplices, actually I've got this huge blackboard, I can draw a picture. So higher simplex will be just composition of just composable arrows and all possible two morphisms. So from, now let's see, from here to here, from here to here, and I think there should be one more. No, that's, sorry?
There should be four if it's playing.
Yeah, okay, I need four arrows. Like if we draw another arrow, then we get more interesting structure, right? So then we get some conditions. Okay, so for any composition of two following arrows, we have a two morphism. So it's built up of pieces like this. So I have two arrows, their composition, and another arrow, and two morphisms from composition to this arrow. And the whole system has to be consistent when you have more of them. And this last condition number 3 just says we have a consistency between all these different two morphisms. So overgluing of compositions and diagonals. Now, so this is a set. So this is a simplicial set. The simplicial nerve is a simplicial set, and its main property is it's a Kant simplicial set. So it has the property that you can fill up the horns You should think of a group. So if I have two group elements, G1 and G2, I can always fill up the missing edge just by putting in G1, G2, G1. Okay? And this consimplicial set is the same notion, just higher dimensional. So filling up horns is you start with a horn like this, and then given the three faces, you can always fill up the fourth face. Just like here, given two faces, you can fill up the third face. Okay? And it holds in dimension. So the nerve is a consimplicial set, and homotopy groups for n larger than 2 equal to 0. In the case of a group, it's still consimplicial set, but the homotopy groups are 0 for n larger equal to. And pi 1 will be your group. Now, a definition. So it's not obvious when two groupoids are equivalent. It's not obvious when two groupoids are equivalent either, but one can do it directly from the definition of a groupoid. For two groupoids, basically the only sensible definition I know is that the equivalent is if their nerves are weakly homotopy equivalent. This means there is a map, simplicial map from nerve of one to nerve of the other, which is isomorphism on homotopy groups. For groups, it's the same as saying the groups are isomorphic, actually. Now, there I think I diverged slightly from Ralph. So there's a notion of a two-groupoid. There's also a notion of bigroupoid, which is basically the same data as two-groupoid, except that the compositions, so remember we had composition of arrows. The part of the data was a groupoid structure, so I could compose arrows. And composition of arrows in groupoid is associative. For a bigroupoid, we will think about composition of arrows which is associative up to an associator. So, so there is a natural transformation which connects, which corresponds to changing the brackets in associativity condition, and this associator satisfies what's known as pentagonal identity. And Ralph actually drew it on the blackboard. Now, somehow the whole story was wrapped up by Daskin, like 20 years ago, who did the following. So what he did was to look at all simplicial Kant sets. And he constructed functors from those to themselves, such that if you look at the nth functor, its identity on homotopy groups in degree smaller equal n, and it kills homotopy groups in degree larger than n. So in particular, the range of pi 2 is the collection of nerves of bigroupoids. So given any consimplicial set, you can produce a bigroupoid out of it, just by using this projection. And again, for two bigroupoids, they would be equivalent if their nerves are weakly homotopy equivalent. So reason that I'm spending time on it is that we will some examples. And sorry?
In what sense is pi 1 the fundamental groupoid construction?
Pi 1 is the fundamental groupoid, literally.
But then it takes a nerve again, so it's the nerve of the fundamental groupoid.
So pi 1 is homotopy equivalent to the nerve fundamental groupoid. When you construct these functors, the construction is somewhat more involved. You get something larger, but it is homotopy equivalent to fundamental groupoid. Okay, so I will want to say something about equivalence of some more or less natural occurring two groupoids. So let's start with those. So one of major sources is deformation theory, differential graded Lie algebras and that stuff. So let's start there. So suppose that we have a differential graded Lie algebra. So it's a graded vector space, it's a graded Lie algebra, it has a differential, and satisfies all the obvious compatibility conditions. Right? So one distinguishes these Maurer-Cartan elements, which are elements of degree 1, which satisfy this Maurer-Cartan equation. It's the same equation that you meet when you start studying Lie groups. There's this fundamental one form on a Lie group, which says Maurer-Cartan equation. This is the equation. Now, so when we start with such a differential graded Lie algebra, we do construct a two-groupoid. It's okay, it's question who was the first one to construct it, but okay. So I think I would call it the lim in this case. So the objects are Maurer-Cartan elements. One morphisms. Let me draw it in a picture. And let me, just to help you, I start with this Maurer-Cartan element of G. Then Maurer-Cartan equation just says there's a differential on my DGLA, and there's this Maurer-Cartan element. And if I think of it as acting by bracket, then Maurer-Cartan equation just says that nabla square is 0. So Maurer-Cartan elements, one can think of the Maurer-Cartan elements as flat connections. Then one morphisms, in this case, so G is DGLA, in particular the 0th degree part is a Lie algebra. If it's nilpotent, we can construct the corresponding exponentiated to get a corresponding profinite Lie group. And this Lie group acts on flat connections by conjugation. Okay, so the arrows are given by action of this gauge group. So exponential of G0. And then two arrows are constructed, so we have the x's which sit in MC1 of G, which is just x G0. Now, since we are in the case where, as I said, G vanishes for degree smaller than -1, the formula in 3, so the bracket associated to A, B, gamma, is the commutator of nabla A and B, so gamma, let's say. This is again a Lie algebra structure on G on terms of degree -1. So if I start with something of degree -1, here I have something of degree 1. Sorry, degree 1, so I have degree 0. Commutator with something of degree -1 is again of degree -1. Okay. So this is a bracket defined on G -1. And we can construct the corresponding group. And these will be our two morphisms, except that they depend on gamma, right? Because bracket depends on gamma. So for each flat connection, we have this group of kind of invariant gauge transformations, and these will be our two morphisms. Okay. Now, okay, this construction will come again and again, but
So should we think of these as something like inner gauge transformation?
yes. Or you could think of x's as vector fields. So you can think differently. You can think of gammas of Poisson brackets. So Poisson by vector fields. You can think of x's as vector fields acting by local diffeomorphisms, and these will be Hamiltonian vector fields.
And on the slide you have written A, comma, delta gamma B instead of what you wrote on blackboard. They are all the same?
It's the same.
Or
It's, no, yeah, no, it is actually the same. Luckily. It is the same. It was commutator of two odd things. So
you want to control deformation theory of the field.
Yeah, for example, right? So you want to control the formation theory, but, well, we will get these DGLAs coming from the formations, of course, in a moment. But in general, actually, you really think about this differential graded Lie algebras, and okay, first example is this two-groupoid. Now, this construction is actually functorial, and actually very nicely functorial. So if I have a morphism of DGLAs, so something that preserves the bracket and differential, linear map with degree 0, which preserves bracket and differential, obviously it induces a map on the corresponding two groupoids associated to Maurer-Cartan elements, and it will be an equivalence of two groupoids. So on the slide, what I did was slightly, well, did the same thing. I just made sure that I have something nilpotent. Okay, so if I start with any DGLA, it's not nilpotent, but if I tensor it with some nilpotent ring, it becomes a nilpotent DGLA. So I can construct these exponential groups. Okay. Generalization of this thing is L-infinity algebra, and unfortunately it will show up, whether we want to or not. So, so like the DGLA has bracket, has differential and bracket, L-infinity algebra is a differential graded algebra up to homotopy, right? So bracket satisfies Leibniz identity up to homotopy, and then there are some high homotopies making things consistent. So effectively it means that you have a bunch of brackets. So you have a standard bracket between two elements, then you get bracket between three elements, and so on. So I wrote more or less explicitly how you can see an infinity algebra. So it's kind of a geometric picture. You look at dual, shift the degree by 1. You see the shift of degree thousands of times during this lecture. But shift the degree by 1, take the symmetric algebra on this. So this is just a graded vector space. So symmetric algebra is just direct sum of symmetric tensor powers, where symmetric means even things commute, odd things anti-commute. Okay? And on this one, just define a delta A. So the symmetric algebra is a co-algebra, so there is a coproduct. Just given A, tensor B, tensor C. Coproduct will just split it into sum of things of this type. Okay? So you can define co-derivation, just dual of a derivation. And this infinite algebra structure is just a co-derivation of this one, which is flat, which satisfies this condition. Precisely the example differential graded Lie algebra. The transpose has two components. There is a transpose of differential, and there is a transpose of a bracket, which is mapped from G star to G star tensor G star. In general, and the symmetric condition just says that bracket is antisymmetric. Okay? So that's the example. And for infinite algebra, I can also introduce a notion of nilpotent. Unfortunately, the definition that's in the literature and that everybody copies is wrong. Okay, so I wrote it here. So you look at all possible brackets, higher brackets of G, and it's nilpotent if you have sufficiently long sequence of higher brackets of anything, when the result is 0. Well, don't need to know much about that one. Now, just like for DGLA, we could define Maurer-Cartan elements, you can do the same thing for infinite algebra. The only difference is that you don't just have a single bracket like here, but you have a bunch of brackets. So, so instead of, so the condition for Maurer-Cartan element was d gamma plus 1/2 gamma gamma equals 0. That was this flatness condition. For infinite algebra, it's not just single bracket, but sum of all brackets that show up in the structure. Now, so again, what's happening is the following. So if we've got DGLA, we have written down a two-groupoid. Now, in general, when you have a, well, an infinity algebra, you can think about the set of Maurer-Cartan elements, and actually there is a natural simplicial set associated to it. The first construction actually is due to Hinich, and then Getzler reproduced it in slightly more general words, which is the following. It's a simplicial set, so for each n we get a collection of n simplices. So the way you construct them is that you look at G tensor, say, polynomial differential forms on n simplex. Well, differential forms is a graded commutative algebra, so tensor product is again an infinity algebra. So bracket of, if you take Lie algebra, tensor commutative algebra, the result is still Lie algebra. The same thing holds for infinity algebras. So you can look at this G tensor differential forms on delta n, and we look at the set of Maurer-Cartan elements. Over a simplicial structure, the simplicial structure, phase, degeneracy maps, this kind of things, they just come from the set that the standard n simplex has simplicial structure. So this is a simplicial set. It is a Kant simplicial set, so has this property of filling up the horns, like before, and has this property that if our G has no terms of degree lower than minus n plus 1, then homotopy groups vanish for degree larger than n. This will be one of the examples. And again, the construction is pretty functorial, so given a quasi-isomorphism of nilpotent infinity algebras, the corresponding simplicial sets become homotopy equivalent. Oops. Next one. Now,
Converse true also?
sorry?
Is the converse true? If you have homotopy equivalence of these things?
No, not necessarily. No, because you cannot, so, okay, I'll say something about it in a second. No, but no, it's not that good. Okay, so suppose we start with a nilpotent differential graded Lie algebra. Okay, so just a DGLA, and assume that it vanishes in degrees smaller equal minus 2. So we constructed this two-groupoid associated to it, and has a nerve, right? So we associated to it a simplicial set, Kant simplicial set. On the other hand, it's also an infinity algebra. We can do a Hinich construction, and we get this sigma G, this other simplicial set associated to DGLA. So the main result, well, at least it's one of the things that you really need, is that the two simplicial sets are weakly homotopy equivalent. Okay? So now I can turn things around and make a definition which makes sense. So suppose I've got a bigroupoid associated to DGLA. Now it's a bigroup nilpotent DGLA, which vanishes in degrees small equal minus 2. It's pi 2, then I can construct the corresponding simplicial set, Hinch simplicial set, use the Taskin construction, and by definition, the bigroupoid is pi 2 over sigma G. Okay? Remember, so what happened was starting with G, I could construct this Maurer-Cartan thing, so our Aladeli. Okay? I could also construct the sigma G, and then there was this construction of this is a bigroupoid. Okay, it has a nerve, but it is a bigroupoid. What I get here is a simplicial space, and then this pi 2 construction produces again a bigroupoid. Okay, so from Kant simplicial sets, we could construct bigroupoids. Okay, And well, this theorem just says that these two bigroupoids are equivalent. So the nerve of this bigroupoid constructed directly here is weakly homotopy equivalent to sigma g, which is basically the nerve of this bigroupoid. Okay? I will need it, well, you'll see very soon. I hope you may.
Why do you need pi 2? Because your first theorem says that sigma g.
Well, pi 2 gives me a bigroupoid. Sigma g itself is a simplicial set. It's not a bigroupoid. Okay?
I thought pi 2 also is simplicial sets with just more composition.
No. This is, well, this is a bigroupoid, right?
So pi 2 is not a retraction, it's just turning a simplicial set into a bigroupoid.
It's a retraction plus construction of a corresponding bigroupoid. So Daskin actually constructs bigroupoid.
But for sigma g there is no retraction necessary because it's already a Kant simplicial set.
It is a Kant simplicial set, but you need a corresponding bigroupoid. He constructs this bigroupoid on the nose. So we do have two bigroupoids. I actually need it because okay, let's get there, right? So, okay, I won't explain this one. I don't think that much time. So yeah, so how you prove it? So actually, you construct explicit map from here to the nerve of this one. And kind of high construction of high holonomic groups. Okay, examples, right? So the first example, and since my talk is somehow about deformations, is of course Hochschild cochains. So we look at the Hochschild cochains. Well, as usual, linear and multilinear maps from A to A are n Hochschild cochains. If we shift the degree by 1, then there is this Gerstenhaber bracket, which makes it into a differential graded Lie algebra. That's where we need to shift degree by 1. So, and will come again and again. So, can you guys see where there's something to clean the blackboard? Oh, yeah, that's good enough. And the shift of degree by 1, degree minus 1 is A, degree 0 are linear maps from A to A, degree 1 are two linear maps from A to A, and so on. And the bracket, Gerstenhaber bracket, is just the commutator of linear maps here. And then bracket between something here and here is just evaluation. Linear map evaluated on A. And automatically the rest follows. There is this differential, which is really commutator, Gerstenhaber bracket with a bilinear map, which is given by the product. And saying that product is associative is the same as saying that this bilinear map is associative. Okay. Well, this is DGLA. We will look at, well, we will normalize things, right? So we will just say that whenever one of these, we look at work with algebra with unit, and whenever one of the entries here is unit, the resulting map is 0. So just to make life easier, again, we look at so these Hochschild cochains form DGLA, tensoring it with some maximal ideal in some Artin algebra, makes it nilpotent. It vanishes in degrees smaller than -1. So we can do our construction, and we get a functor from these Artin algebras. So again, from this, again, the reason for these Artin algebras is that I want nilpotent things. Okay, so if I start with DGLA, I tensor it with something nilpotent to make sure that I have something nilpotent again. Okay, so you get a functor from R, which is just a commutative algebra of maximal ideal, nilpotent ideal MR to these two groupoids. Deformation. So this is really an example of deformation. It's such a thing. So what is a deformation? I start with an algebra with some product, right? And a deformation will be, I will take A tensor R with some coefficients. Well, think of R, doesn't have the easiest one, it's just formal power series in the parameter. The maximal ideal here is H. This one. So the deformation of this algebra is really a product on A, which is M tilde, product on this one, such that M tilde modulo of this maximal ideal is my original product. Okay? Well, product is a bilinear map. So this M tilde in this example is M tilde, product tilde is, okay, sorry, let's write I here so we don't mix product and M. So this is M plus H times something. Well, this something is a bilinear functional, so it really lives in our Hausdorff cochains of A, well, tensor coefficients, so let's form a power series. But it has H in front of it, so it lives in here. Okay? So this correction term lives in here, in my DGLA, well, tensor ideal. Now, as I said before, Merrill-Cartan condition is just saying that the corresponding bilinear map is associative. Right? So Merrill-Cartan condition on the correction is the same as saying as that this is associative. Okay? So Merrill-Cartan elements in here is precisely the same as deformations, associative deformations of a product. So deformations of my original algebra. Okay. So there is this, again, two categories of products on A. R products, so objects are just R star products, I called it, so these deformations of original product. One morphisms, just linear algebra morphisms which, just linear morphisms which transport one product to the other. One of the star products to the other, and two morphisms will be, as Ralph was saying, kind of inner automorphisms. So just intertwiners between two linear maps. This is again a two-groupoid. Unfortunately, the last thing vanished. And, well, as I said, associativity of this deformation product is the same as with Merrill-Cartan equation. So this deformation category of an algebra is an isomorphic to Maurer-Cartan two-groupoid of corresponding GA. So DGLA of Hausdorff cochains, well, tensor the ideal. So whether we study deformations or whether we study this Merrill-Cartan two-groupoid, it's the same. Oops, running out of it. So example. So I won't be able to go through all of it, but so example is if we think about smooth manifolds. That's the insight of Kontsevich. We write down another two-groupoid. So first of all, we write down polyvector fields on X, I guess. Look, sections of the value of polyvector fields. There is the Schouten bracket here, and there is zero differential. Again, this, as I said, shift of degree by 1. So functions are of degree -1. Vector fields are of degree 0. Commutator of vector fields is a vector field. Okay? So this is a differential graded Lie algebra. You can write down corresponding Maurer-Cartan groupoid. It's two groupoids. So as I was saying before, so here Maurer-Cartan elements are Poisson brackets. So elements of degree 1 in here. So bivector fields which satisfy Maurer-Cartan equation. So the differential is 0. Maurer-Cartan equation just tells me that they commute with themselves, so they are Poisson structures. The morphisms are given by vector fields, and two morphisms are just given by functions. Okay? And on the other hand, I can look at C infinity of x, and this, as I noted, G. So this is this DGLA of Hochschild cochains. And we will just look at local Hochschild cochains. So one's given by, so Hochschild cochains are multilinear maps from this algebra to itself. We'll just assume that they are given by multi-differential expressions. So some differential operators. It's equivalent to requiring certain kind of continuity. And it's another DGLA. And so if I look at, again, put in coefficients for my power series, okay? Now, the basic statement is that these two are, there's an L infinity quasi-isomorphism between those two. That's Kontsevich. This means that the Maurer-Cartan 2 groupoid is equivalent to Maurer-Cartan 2 groupoid here. Maurer-Cartan 2 groupoid here is given by Poisson structures, vector fields, and functions. Maurer-Cartan 2 groupoid here is given by star products, equivalence of star products and isomorphism of star products and intertwiners. And the general statement, since we've got L infinity quasi-isomorphism, the two Maurer-Cartan groupoids are equivalent, so star products are classified by Poisson structures up to natural equivalence. Okay? Well, precisely what one does is that one constructs a third DGLA and shows that it's quasi-isomorphic as L infinity algebra to both of them. And that's general construction. Okay? So you should think a minute that if I've got two differential graded Lie algebras, then I can have a map between them which is L infinity morphism, but not DGLA morphism. Okay, it has a bit less structure. So I'm using different structure on them. So the L infinity morphism between DGLAs is not the same as DGLA morphism between DGLAs. There are more of them. There's more space for it. Okay, so I wanted to talk about the deformations of ZERP stacks, the stuff. So what is a stack? So in general, you'll get an easier picture in a minute, but okay, I'm running out of time. So it's kind of data that's pretty useful. There are different ways of defining stacks, and you see a lot of things in literature, but at least I prefer to have something concrete to work with. So a stack on X is some manifold, smooth manifold, or complex manifold, or stack. So it's an open cover. On every open set, we have a sheaf of rings. Then on intersections of a cover, we have isomorphism between these sheaves of rings, or the restrictions to intersections. And on triple intersections, well, these isomorphisms that we have, they don't glue together, but they glue up to an inner automorphism. Okay? And these inner automorphisms have to satisfy the obvious cocycle condition. There's an obvious notion of isomorphism of stacks, or morphism of stacks, and the best way to understand it, if you sit down, close yourself in your room, make sure nobody looks at you, sit down and try to formulate it, because formulas become long. But they don't really introduce any more problems. So ZERP is a special case of stack when our sheaves of rings is just smooth functions on open sets. So locally, we look at the smooth functions on UI. On intersections, you just take smooth functions on UI, uj, restricted, they are supposed to be equal. So these transition maps are identities. But there is still this Cijk, this Tukosaiku left, which does not have to be trivial. Right? It's just an inner automorphism. It can act trivially, but does not have to be trivial. Well, it's non-trivial in general. So for ZERP, it's non-trivial, just a Tukosaiku. Everything restricts to a Tukosaiku on X with values in the invertible functions.
So the stack on a point is just any algebra? There is no restriction on the algebra?
In principle, there is no restriction on algebra in general. And actually, this data is called daily intercept data. But that doesn't really matter. So example that a lot of you know, bundle of compact operators on a space. So locally, this bundle is trivial. So locally, the bundle is a form open set cross compact operators on H. On intersections, we get, well, transition functions. There is only one copy of compact operators on separable Hilbert space. So on intersections, we get some intertwining unitaries. On triple intersections, we get, we get a product of three unitaries which implements trivial automorphism of compact operators. It does not say that the product is one, just says that the product is a scalar. So we get our familiar description of a bundle of compact operators. Another way, categorical way of saying the same thing is for each open set, we have a sheaf of categories. Like what? So first of all, on open set we get sheaf of categories, on intersections invertible functor, and on triple intersections natural transformations which satisfy obvious compatibility condition. A ZERP will be in this case, so we have a sheaf of categories which are categories of representations of compact operators. It's fairly trivial because there are very few representations of compact operators, so it's very simple. And all this data reduces to standard notion of bundle of compacts or to standard notion of a ZERP.
Is it just categories or groupoids? You don't want sheaf of groupoids?
Now, when I get free groupoid. No, I don't want sheaf groupoids here. Well, groupoids are good, well. No, sorry, you meant groupoids. Groupoids are fine. But it's in general categories.
You don't assume
I don't assume that my arrows in these categories are invertible. I don't have to. Okay, so given such a stack, well, not a stack, but let's think about the ZERP. So given such a ZERP, we can ask about the deformation and direction of a ZERP. So just as before, locally we have a sheaf of vector spaces with locally we construct deformation of a product. So locally we have a star product. On each open set we have a star product. Now it's non-abelian algebras, right? And on the intersections we have some local isomorphisms, which modulo H are identities, but these are just formal, think of just formal vector fields, okay? And on triple intersections, we get a Tukosaiku, okay? These things show up in real life, by the way, okay? So now I wrote it here, but they really show up. So again, given X, given a stack, or given a ZERP or a stack, we get a functor with this functor which from Artinian local Artinian algebras constructs two groupoids, the deformation groupoid, right? Again, these Artinian local algebras are there to make sure that things converge. Okay, I don't get infinite sums in these constructions. That's the only reason for those. So there is a matroid construction, kind of matroid construction which controls deformations of a ZERP. So what you do is basically you write down the algebra, the groupoid of the covering groupoid of our cover UI, right? So we have locally, so we write the matrices with, where in ij place we have functions on UI intersected uj. Then the product is like product matrices, but twisted by the cocycle. Okay. So this is an algebra. You can construct its GA. So look at Hochschild cochains on this one, and this does control deformation of a ZERP. So if you could study this one, if you could study these Hochschild cochains, you could really describe deformation of a ZERP. The problem is that you can't really work locally in this one. You should think about the problem of support conditions. So you have to think about the problem that we need functions with compact support, so local things cannot be extended. So that's not the one to work with. Okay, I don't have much time. I lost a few minutes, but I don't have much time. So we do the following. So let me just say a few things. So instead of thinking of this matroid algebras, you look at jets. Okay, so I've got this manifold X, and I can look at jets on this manifold. So basically, jets are things which map differential operators to functions. So jet of a function just tells you you have a function, you take some differential quotients of this function and tells you, and then you can compute the result at a point. In general, jet is something which does precisely this. Takes differential operators and maps them to functions. It has a product, because differential operators have coproduct, jets are dual to differential operators, so they have a product. So since they are these linear maps from differential operators to functions, they have a very natural flat connection. So space of jets has a flat connection. Just given a differentiating direction x just means taking L and commuting it with x. If D is differential operator, xd is also a differential operator. Okay, and L of D is a function, x, so vector field x on a function, and again produces a function. So this expression defines a connection. There's no pointer here, is there? No. Okay. Can I make it visible here? Yeah, oh yeah, here. So this defines a connection. Actually, it's flat connection. Its square equals 0. Locally, this jet bundle is very simple, just smooth functions, tensor formal power series in, formal coordinates, x1, xn. This canonical connection is also very simple, just the RAM differential minus sum of differentiations along formal coordinates times dxi. So there's this canonical one form acting on both with values differentials here. In particular, just so that you know, so a flat jet, so a jet such that delta L is 0 is the same as jet of a function. And conversely, a function, you have a jet of a function if and only if it's flat. So what we will do is, instead of looking at this huge matroid algebra, we just look at jets of functions. So this bundle of jets on our manifold, we take Hochschild cochains in the jet direction only. So I have functions, and fiber-wise I have these formal power series, these jets. So I will take this Hochschild cochains, so linear in the space direction, but Hochschild cochains, so multilinear in fiber direction. Again, it is a DGLA. there is a connection, there's this canonical connection which commutes with over Hochschild differential and commutative structure in vertical direction. So I can write down a differential graded Lie algebra. So I can look at differential forms on the base, coefficients, Hochschild cochains in fiber direction. I have a differential, which is this canonical connection, plus Hochschild differential. There is a bracket, and I get a DGLA. And this one actually controls, again, this controls deformations of smooth functions on X. Now, now we are thinking about the formation of a jet, so we want to twist. So we are twisting the structure of smooth functions. So it's very simple to twisting. We don't see it on functions. The only thing we see is the Tukosaiku. When we go to the deformation, we actually see more structure, so more things get twisted. And the way we see this twisting in terms of these jets is, well, there's an extra differential. Okay, I won't have time for this one. But let's try to go here. So what comes out of this jet is that there is an extra two-form on X with values jets that you can construct from the class associated to the Zerb. And what's happening is that the differential on this bundle of Hochschild, jet-wise Hochschild cochains, differential gets twisted by in contraction with this two-form. There's a natural way of contracting this two-form. And, oh God, no, it doesn't quite work. So again, this differential graded Lie algebra, so Lie algebra of differential forms from the base, Hochschild cochains of jets along the fiber, with differential twisted by this two-form, controls deformations, or Zerb deformations. So Maurer-Cartan elements of this object here will control the Zerb deformations of my algebra of smooth functions. Well, that's what I just said, this last theorem here. And then, let's forget this one. Now, so the final outcome is, so now we got this twisted, kind of twisted algebra, of differential graded Lie algebra of fiber of differential forms with coefficients, Hochschild cochains in the jet direction. Well, it's DGLA, it controls deformations. Unfortunately, in distinction to this nice picture of Kontsevich. So we got an analog of this one, but somehow twisted version. So, but still DGLA. Okay? Unfortunately, this one doesn't work anymore. So the analog of Kontsevich results, the formality result, as it was actually, the notion of formality was actually introduced by Sullivan before. And Sullivan said that DGLA is formal if it's L-infinity equivalent to its cohomology. That's what happens here. This is not true anymore. Instead of just getting, so let's twist this one. What's going to happen here that we don't just get polyvector fields, we don't get DGLA of this type, but we get an extra structure. So differential is still 0, but we get an L-infinity algebra instead. So there's an extra operation. How did I write it? Phi. Well, yeah. Okay. So there's an extra operation. So remember, it's DGLA. So it has, to begin with, there's no differential, there's bracket. There's also ternary bracket associated to this one. And it's fairly easy to imagine. So let's think for a second. So we have a verb, with corresponding to cosaiku, via diximia duadi, via boundary map, there will be a class in free cohomology. Right, so to this omega, we can associate a class in H3 deram of M. Actually, X. Actually, in general, with it's a class coming from H3 with coefficients in Z, but it's a class, cohomology class. Think of it as cohomology class. So free form. Now, the ternary operation associated with this free form, so pi 1, pi 2, pi 3, this omega, is as follows. So I've got three Pauli vector fields. Okay, this is a free form. It has three differentials. It's 3 times I see some df, dg, dh. Okay, so what happens? You take each one of these differentials and you contract with one of these vector fields. Okay, so this is something from n1, n2, n3. So it's n1, n2, n3 vector fields. The result is n1 plus n2 plus n3 minus 3 vector fields. Okay. So this ternary bracket gives an L-infinite algebra structure here. So it satisfies all the compatibility conditions you need. And these two are in fact L-infinite equivalent. So there's a L-infinitymorphism, which is a quasi-isomorphism. Okay? So in particular, the deformations, since this one controls the deformations of Gerb deformations of smooth functions, the deformations and these are the same as Maurer-Cartan elements here. Equivalence class of Maurer-Cartan elements here are the same as equivalence class of Maurer-Cartan elements here. And this is, well, explicit actually, so that's the condition. So the Maurer-Cartan element here is it's not a Poisson structure, but it's a bivector field, something of degree 1, which satisfies Maurer-Cartan equation. So the commutator is, well, this triple bracket. I think I'll stop now. I'm out of time. Yes, over smooth functions. Yes, they do. Over smooth functions, yes. Yes, they do. Luckily, they do. Otherwise, most of analysis would vanish.
It's a small.
Sorry?
It's a small point.
No. They do very much. It's a coproduct over smooth functions, but yes, very much they do. Believe me, it's well, you can imagine yourself, right? If you try to write it down.